In this video, I want to go over what are sometimes called the fundamental trigonometric identities. But before I do that, I want to emphasize that in order to be successful in trigonometry, the main prerequisite is that you have a very good foundation in college algebra. A lot of things that you do in college algebra, as far as solving equations, simplifying rational expressions, you're going to do in trigonometry. Okay, solving equations in trigonometry, simplifying expressions involving the trig functions, and so forth. That requires a sound foundation in algebra. Okay, so the basic definitions of the trig functions are one of the first things that are given. Geometry, or trigonometry, as you say, involves the study of triangles, the sides relative to the angles, solving equations, word problems involving quite a few concepts, law cosines, law sines, and so forth. But in this case, we're going to focus strictly on the fundamental trigonometric identities, and then go over some later on, maybe another video, go on to the proof or verification of identities. Okay, so let's just look at these first. The first one is called the quotient identities, for obvious reasons. Tangent of theta is defined by sine of theta over cosine of theta. And the cotangent of theta is defined as cosine of theta over sine of theta. Okay. And then we have the reciprocal identities. Cosecant is 1 over sine. Cosecant of theta is 1 over sine theta. Now again, that implies several things here. That also implies, should be obvious to you, that you could also say that sine of theta is equal to 1 over cosecant of theta, right? Or that's the same thing as saying cosecant theta times sine theta is 1. Okay, so those are implied. The next one says secant of theta is equal to 1 over cosine of theta. Again, it's implied that cosine of theta is equal to 1 over secant theta. And also the product of secant theta cosine theta equals to 1. Those are all implied from that. In the same way, for the third one here, cotangent of theta is 1 over tangent of theta. So again, we can also say the tangent of theta is 1 over cotangent of theta. Or the product of cotangent theta and tangent theta is equal to 1. Okay. The other ones are called the Pythagorean Identities, again, because of the look of a squared plus b squared is equal to c squared. I can write all of those like that. If I put the square on the 1, you can see the similarity to a squared plus b squared is equal to c squared. Okay. Now, on this one, I want to show you again how we sometimes verify identities. A lot of times you're given basic definitions, you're given other identities that you prove using those basic definitions. So in this case, for example, let's suppose we verified that the first identity is true. So let's suppose, okay, this is given. We know that's true. It was verified. Okay, let me use structure prove this to you. And then he or she tells you, okay, if I know that this is true, use that plus whatever's given up here to show that the second one is true. Okay? How could we do that? Well, one way we could do it is say, well, let's divide both sides by cosine squared of theta. Okay, so I'm just going to put it, everything over here is divided by that. And then this side is also divided by cosine squared theta. Okay. Okay, so now sine squared over cosine squared that should be obvious if that's the same thing as sine theta over cosine theta, quantity squared. But sine theta over cosine theta, by that first identity over here, is tangent theta. Okay, so this becomes tangent squared theta. And of course, cosine squared theta divided by cosine theta. Cosine squared theta is 1, so there you have that one. That's 1 there. And then, of course, on the other side, on the right side, 1 over cosine, because secant and cosine are reciprocals, 1 over cosine squared should be the same thing as secant squared. Okay, basically from this identity right here. Okay. Now, if I wanted to prove that the third identity is true, then I would just divide through by sine squared. So I divided this, well, not this one, but let me clear this out. Then I would just take this right here and divide both sides by sine squared theta. And then this side divided by sine squared theta. And then you can see then that sine squared theta divided by sine squared theta on the left side is 1. Okay, so that's that one right there. And then cosine squared divided by cosine squared divided by sine squared theta. Cosine squared theta divided by sine squared theta. That, of course, will be the cotangent squared theta. And then on the right side, 1 over sine, because the sine function and the cosecant function are reciprocals, 1 over sine squared should be the same thing as cosecant squared theta. And that's how you would verify the identities. Okay, so one of the main topics that you have in trigonometry is verifying a particular identity, or sometimes I say prove that this identity is true. So let's cancel this, and then the last ones are called even odd identities. Okay, so this is saying that if you have sine of minus theta, that's going to be the same thing as minus sine theta. Cosine of minus theta is the same thing as cosine of theta. Tangent of minus theta is equal to minus tangent of theta. Okay, and over here at the bottom, cosecant of minus theta is equal to minus cosecant of theta. Secant of minus theta is equal to secant of theta. Cotangent of minus theta is equal to minus cotangent of theta. Okay, so this is the same thing as we have with functions. Okay, regular functions. So if I have a function f of x, okay, and I evaluate this function at minus x, which is what this is. In this case, I'm using theta instead of x, but it's the same thing for functions. Regular functions use x usually. Okay, so if f of minus x is equal to f of x, in other words, if I evaluate the function at minus x and I get back the same function f of x, then that function is said to be even. If I evaluate a function at minus x and I get the opposite of the negative of the original function, that function is said to be odd. Okay, very basic example, and here we're just dealing with regular functions. So let's suppose I have f of x is equal to x squared. That you should recognize as a parabola with vertex at the origin. Graph looks something like that, okay? U-shaped with the origin being the vertex. This is considered an even function. Now, in terms of the graph, we can say that an even function is symmetric with respect to the y-axis. y-axis. Okay, so even functions have symmetry with respect to the y-axis. Notice it's a mirror image here. If I flip it over the y-axis, I get the same thing back. Okay. Now, if the other thing happens, if f of minus x equal to minus f of x, then I've got an odd function. So let's look at, say, f of x equal to x to the third. Okay. Now the graph of that cubic function is going to look something like this. Okay. It'll look something like that. So if I replace the x by minus x, I replace the x by minus x. Notice on the other side that'll give me minus x to the third, but minus x to the third is still going to give me a negative x. So it gives me the same function back, except negative. Okay. So again, even functions like f of x equal to x squared will be symmetric. The graph will be symmetric with respect to the y-axis. And odd functions like f of x equal to x to the third will be symmetric with respect to the origin. Okay, so we will rotate this, say, 90 degrees. I'm sorry, 180 degrees. Okay, I get the same thing back. Okay, so looking at this then, based on this on this right here, and this right here, we can conclude that the sine function, the cosecant function, the tangent function, and the cotangent function are odd functions. That is, the graphs are symmetric with respect to the origin, whereby this here and this here, the cosine function and the secant function are even. Okay, so the cosine and the secant function are even, symmetry with respect to the y-axis, and the other four are odd, symmetry with respect to the origin. Okay, so we'll pick it up here in the next video with verification of some identities using these fundamental ones here. So thanks for watching, and we'll see you next time.